Hi, welcome to another lecture on deep learning. Before we look at recurrent neural networks as a deep learning model for sequences, we want to study a particular type of sequences, namely language, which we will use as a motivating example. We will also look at properties of language and traditional approaches to modeling language. So the first thing that we need is we need to define our sequence features or tokens. Those could either be words, they could also be characters, they could be syllables. So let's for now stick with words. For example, a sentence would be a sequence of words, W1, W2, and so on, up to WT. Because we want to model the language, this word is the output or the label at this particular time step. And a language model is a model that models the joint distribution of the whole sentence, starting with the first word, the second word, and so on until the end of our sequence. If we have a good model for this distribution, then an ideal language model would allow us to generate text by drawing words. And it would draw words from this conditional distribution where we have the conditional distribution of the next word at time step little t conditioned on the word before, and so on and so forth up to the first word of a sentence. If this model was perfect, it would actually allow us to sample just by sampling from this conditional distribution. And then once we have sampled, use that to condition again. You get a new conditional distribution for WT plus 1 and so on and so forth. You would actually get proper language, a natural language, for example, a piece of English text. It would allow us to generate a meaningful dialogue by conditioning on previous fragments of such a dialogue. Now, obviously, this is quite a hard task and it's actually not possible because we would really need to understand the text in order to generate such natural language. So just generating grammatically sensible content would not be enough. So let's look at what's actually possible using language models. We could, for example, use them in order to improve a speech recognition system. Say you have a system that takes a voice sample and outputs a sequence of words. Of course, there are several proper word sequences that are different but sound very similar. For example, to recognize speech and to recognize speech sound very similar, and both map to proper words. However, a language model would assign a much higher probability to recognize speech, and thus would help us to solve this ambiguity between two proper sequences of words. So it can help us to generate text from speech if combined with such a speech recognition model. Or we could use language models in order to summarize texts, and we would, for example, find the phrase dog bites man to be much more frequent than man bites dog, even though both are proper words, both are grammatically correct, but usually men do not bite any animals. If we would look at the phrase, let's eat grandma, a proper language model would actually tell us that this comma is important. So if we model the comma as a word, it would recognize that having the comma there gives us a more sensible sentence than if we leave out the comma and would say, well, let's eat grandma. The language model models this joint distribution by factorizing the sequence over the time steps. So starting at t equals 1, we get the marginal distribution of the first word. Going to t equals 2, you get the conditional distribution of the second word conditional on the first, and so on and so forth until you reach the last word. For example, for the sentence statistics is fun, we would consider the full stop also as a word. We would start with the marginal distribution of having statistics at the beginning of a sentence, then is following statistics, so the conditional distribution of is, condition of word statistics before, times the probability of fun given statistics and is, times the probability of a dot ending the sentence after statistics is fun. Now the question is how we get these conditional distributions, or all of these distributions. So the probabilities are now the parameters of our language model. Consists of the marginal word probabilities and the conditional word probabilities of WT following the sequence of WT minus 1 and so on. Typically, we use training data in order to model these parameters. And these training data are usually large text corpora, such as Wikipedia, Project Gutenberg, or web pages. And the word probabilities can be estimated from relative word frequencies in these corpus. For example, P of statistics could be estimated as the frequencies of sentences starting with statistics. An alternative modeling strategy, and remember, in order to get a model, we have to do these design choices or modeling choices, and some of them may be better and some of them may be worse, depending on our applications and assumptions on the problem that we're modeling. An alternative way to looking at the frequencies of sentences starting with statistics would be to count the occurrences of the word statistics in the whole text or corpus and divide it by the total number of words in this corpus. Both of these give us a form of frequency. Now, of course, we would need a larger corpus in order to do the first one, because there will be fewer sentences starting with statistics than just occurrences of statistics in the same corpus. But in order to model sentences starting with statistics, the first one may be a better fit. Now there's this trade-off between getting more observations and thus getting more accurate frequencies, and something that better fits our applications. So if the corpus is too small, the first one would just not yield accurate frequencies. And the second one particularly works well for frequent words. Now these conditional distributions we also get using word frequencies or word counts. For example, if you want to estimate the conditional probability of is following statistics, then we would look at, for example, the number of occurrences of these combinations of statistics followed by is, dividing by the occurrences of statistics. So we would see how often does is follow statistics compared to the number of times that we see statistics. Similarly, we would go about for triples, quadruples, and so on, where we would divide by the sequence of words, or the number of times we see the sequence of words that we're conditioning on. Now, of course, if we look at longer sequences, then the number of occurrences will be less frequent. This is similar to comparing just occurrences of words to sentences starting with a particular word. The more complex the phrase or sequence is, the less frequent, of course, it will be in our corpus, thus making estimation harder. In order to deal with these small frequencies, one approach is to use something similar to Bayesian modeling using priors. This is called Laplace smoothing, for example, where a small constant ei is added to all counts for sequences of length I. So this can be seen as, for example, a prior probability in a Bayesian model. And the occurrences would just be the likelihood coming from the data. So if m is the total number of words, instead of looking at the mere frequencies of a certain word, where you would estimate the marginal pw as the number of times you see that word plus e1 divided by m, and divide the thing by n plus e1. Similarly, for the probability of a word w prime following w, in order to get to the conditional distribution, we take the joint and divide by the conditional. So we take the number of times we observe the sequence w followed by w prime plus our sort of small prior smoothing, e2 times p of w prime, divided by the conditional word, the number of times we observe w, plus e2. Similarly, for a third word following the sequence w prime and w, the probability of that is the number of times we see the whole sequence w prime, w prime prime, plus e3 times p of w prime prime, divided by the sequence that we are conditioning on, w prime, plus e3. So by adding these small constants, we deal with the fact that sometimes these n's are either 0 for very rare or for longer sequences. Now the downsides of Laplace smoothing is that we need to store all the counts. So we need to store the counts of the individual words, we need to store the counts of sequences of a certain length. Further, it completely ignores context and meaning of words, because it only looks at occurrences of sequences directly after each other. The frequencies of very long sequences are hard or even impossible to estimate. N-grams are Markov models for sequences. So remember that we introduced the Markov assumption as the assumption that in a sequence of a certain length, the conditional distribution of a word t plus 1 only depends on the last so many words, where so many is a parameter that defines the order of the Markov model. For example, in the first order Markov model, we would assume that the word at t plus 1 only depends on the word directly before it. In a second order Markov model, we would make the assumption that p of w t plus 1 depends on wt and WT minus 1. So on the two previous words. Which means that it's independent of all the other words before, which means that if we look at the conditional distribution of the next word, given the whole sequence before that, is equal to the conditional distribution only up to the order of our Markov model, which is the assumption that we put in that simplifies this conditional distribution. And the higher the order, the longer these dependencies are. This model allows us to make a certain number of approximations. So assume we use a 0th order Markov assumption, which corresponds to a unigram model, then the probability of the sequence W1, W2, W3, W4 would just be given by the product of the marginal word probabilities, because the conditional distribution of W4 conditioned on W3, 2, and 1, for example, equals just the marginal, because we assume that in a 0th order Markov model, W4 is independent of everything before it. And in a bigram model, which corresponds to a 1st order Markov model, we would assume that W4 only depends on W3, but not on W2 and W1. Thus, our joint distribution becomes P of W1, the first word, times P of W2, given the previous word W1, times P of W3, given the previous word W2, and P of W4, given W3. Or in a trigram model corresponding to a 2nd order Markov property or Markov assumption, we would assume that the sequence of W1 through W4 is given by the probability of W1, the first word, P of W2 given the first word, times P of W3 given the two words before, and then in P of W4 it's actually starting to be a simplification, because P of W4 does not depend on W1 anymore. So in order to look at properties of text, let's look at an example corpus, namely Time Machine by H.G. Wells. What we see here in this plot is the index of the words, where the words are sorted by the number of occurrences. So here's the index of the word, starting with the first word and then going to the thousandth word and so on a log scale. And here we see the number of occurrences. And we observe that, except for the start here, this plot roughly follows a straight line on a log scale. So Time Machine is a relatively small corpus of only 30,000 words, and the word frequencies decay in this particular fashion. So it's a straight line or linearly on a log plot. The first few words here, those are so-called stop words, where stop words are very frequent words that tell us very little about the meaning of a sentence or so on. So these are words like the, I, and of. Those are the 4 most frequent words in this corpus. And starting there, the remaining words lie on this straight line in the log plot. And this particular behavior in the decay of the words is known as Zipf's law, where the number of occurrence of word X is proportional to, so the sign is proportional to, which means that, so if you wanted to write something that is equal to this, we would, for proportional, multiply by a constant. So that's the meaning of this sign here, that we are multiplying by an arbitrary constant. It means that x plus c minus alpha. So x is the order of the word. This is x here. It's the rank of the word. And n of x is the number of occurrences of that word. So it means that the number of occurrences is something like x to a negative power. This is equivalent to saying that log of nx equals minus alpha, so this is the slope here, minus alpha, times log of x. And here we actually are on a log-log plot, so this is what we're seeing here. So this is the slope here, minus alpha. Now a downside of modeling the word frequencies which have this particular behavior using these approaches based on counts and smoothing is that the smoothing will lead to significant overestimates of the frequencies of infrequent words because we're always adding this constant, where in reality the frequencies actually decay in an exponential fashion. Now if we look at sequences of short lengths, then we see a similar plot. If we look, for example, at our words as before, so this is the distribution over 30,000 words and the distribution of bigrams and the distributions of triples, then the general observation that we see this straight line on a log-log plot still exists and is still the same. Just the exponent alpha is changed. So here we have alpha 1, alpha 2, alpha 3 as the slope. Sequences of words also follow Zipf's law apparently, just with a lower exponent depending on the sequence length. The second observation that we can do is that even though, of course, if you start out with 30,000 words and you look at the number of combinations of these, that you only observe a small fraction of the possible combinations. This points us to a highly non-uniform distribution of these sequences, where some sequences are used very frequently and some are not used very frequently, and apparently also frequent combinations of sequences, which is due to the structure that we have in language. And structure usually is something that machine learning models can exploit in order to model better. Just working with counts would ignore this sort of structure. So that's what would motivate a model that works with something different than counts. And we will see that the recurrent neural network is such a model. The other thing is, again, many n-grams occur extremely rarely, which makes these smoothing approaches again unsuitable because it would highly overestimate the frequencies for these rare words. So this gives us a lot of motivation to look at different approaches for modeling languages, which will be the recurrent neural network. Let's summarize. N-grams model long sequences by truncating the dependencies because they make a Markov assumption of a certain order. We observed that long sequences occur very rarely or never, which requires smoothing if we work with word counts. However, if we actually look at the empirical distributions, then we see that words and n-grams, their distribution usually follows Zipf's law in language, which means that there is this straight or linear decay on a log-log plot. And that means that if we actually apply these smoothing approaches, we would highly overestimate the frequencies, making, again, smoothing on the one side a requirement if we work with word counts. However, a bad modeling choice. And with this, I want to conclude for today, and I hope I provided enough motivation in order to look for different ways for modeling languages, which we will see in the next lecture on recurrent neural networks. Bye bye.